All right, so let's talk about infinite series. So this video will continue what we talked about. So 11.1 was about infinite, or it was about sequences, infinite sequences, I guess you could say. Infinite series are where we are trying to add the terms of the infinite sequence and get a sum. So we have this expression a1 plus a2 plus a3. So these are the terms of the infinite sequence. We're going to add them all up. And so we can use this notation here. This is the summation notation. So the sigma represents sum. We're going to add all the terms from n equals 1 up to infinity. And so the rest of this chapter is really about if we have an infinite series, can we add these terms up and get a finite number, or does it converge to infinity, or diverge to infinity, I should say? And at first glance, you might think, how can you add up an infinite number of terms and get a finite number? Because if there's infinitely many, it seems like eventually you could add up enough to that it will go to infinity. But let me give you a very easy example. So this is an infinite series that converges to a number that does not go to infinity. So 1/10 plus 1/100th plus 1/1000th, then over plus 1/10,000 plus 1/100,000, so on. What is this number? What does this series converge to? So if we look at the decimal form of this, 1/10 is 0.1, 1/100th is 0.01, 1/1000th is 0.001, and so on. Now, if we just add up these three, we can start to see the pattern. So 0.1 plus 0.01 plus 0.001 is 0.111. And you can imagine if we have 1 over 10,000, that'd add another 1. 1 over 100,000, that'd be another 1. And so on. So this is just 0.1 repeating, or we could write this as 1/9. So this infinite series equals 1/9 when you add up an infinite amount of terms. So that's a very simple one to see, but it just goes to show you that you can add an infinite number of terms and get a finite sum. And so they can't always do that. Of course, if you add up 1 plus, even just 1 plus 1 plus 1 infinitely many times, that goes to infinity. Or, of course, 1 plus 2 plus 3 plus 4 infinitely many times goes to infinity. So not all sums will add to a finite number. Some sums will, and so the rest of this chapter is really about learning different methods for deciding if a series converges or diverges. And so we defined those terms in the last section when it came to sequences. They really kind of mean the same thing. They do mean the same thing. Now, how do we decide if a series is convergent or not? We're going to talk about what's called the partial sum. So the nth partial sum, we're denoting that by S sub n. And that is just going to be the sum of the first n terms. So S sub n, we are adding up the first n terms. So S sub 3, for instance, would be a sub 1 plus a sub 2 plus a sub 3. So we're just adding up a finite number of these infinite terms, the first n terms, however many we want to take. If the sequence is convergent, so if these terms in the sequence converge to something, so a sub n, or S sub n, I should say, converges to something. The limit as n goes to infinity equals s, that exists as a real number, then the series is convergent, and we can say that the infinite series would equal that sum. Otherwise, we could say the series is divergent. So let's look at one example, what's called the geometric series. Now, you've probably seen in an algebra class, pre-calculus class, a geometric sequence. So the geometric sequence is, for instance, we could say 1/2, 1/4, 1/8, 1/16, so on. So there are arithmetic sequences where you're adding a constant to each previous term. Geometric is where you're multiplying. Another one, we could say 3, 9, 27, 81, so on. So whatever number you're multiplying each term, the previous term to get to the next term, That's called the common ratio and is usually denoted by R. And so then if you add up all these terms up, so you add up all these or all these, that's called the geometric series. And so we could write this in short notation as the sum of AR to the n minus 1. And of course, we're starting with R to the 0 plus AR and so on. So there's a formula for this. I'll prove the formula. Just kind of show you where it comes from. You don't really need to memorize the proof, but if you're interested, then we'll see it. So let's start with the partial sum S, and we will look at the first n terms. So that will take us to AR to the n minus 1. Then what we're going to do is multiply this equation by R, the common ratio. So that gives us AR plus AR squared plus AR cubed all the way up to AR to the n. Now what we're going to do is subtract these. So S minus RS. So we get S minus RS on this side. Now what do we get on this side? We get A. Now we're going to subtract each of these terms. So notice that we have AR minus AR. We have AR squared minus AR squared, AR cubed minus AR cubed, AR to the n minus 1 minus AR to the n minus 1. And then we're left with minus AR to the n. Okay, so now let's see if we can solve this for S. So let's factor out the S. We get S times 1 minus R. We can factor out an A over here. That's just going to make the formula look a little nicer when we're done. And then we'll divide by 1 minus R. So we get that S equals A times 1 minus R to the n over 1 minus R. Now, if we take the limit to infinity, so let's find the limit as n goes to infinity of S. So that's the limit as n goes to infinity of A times 1 minus R to the n over 1 minus R. Well, if obviously looking back at this one, obviously when we add up all the terms of this, it's going to go to infinity. Now, this one, maybe not. So this one is starting to kind of look like that 1/10 plus 1/100th plus 1 over 1,000. It's going to be a little bit more. The terms are all more than those terms in that other sequence or series. But maybe it goes to a finite number. So let's say that R is less than 1. The absolute value of R is less than 1. So we're in this situation. Now, if n goes to infinity and R is less than 1, that tells us that R to the n is going to go to 0. So you can see that so if R is 1/2, these numbers are going to 0 as n gets larger and larger. Okay, so R to the n is going to go to 0 if the absolute value of R is less than 1. And so that means that that's going to go to 0. So then we just have 1 over 1 minus R times A. So we could write A divided by 1 minus R. And so whenever R is less than 1, absolute value of R is less than 1, we can find a sum. This is convergent. If R is greater than 1, then we're in this situation where the number is just going to get bigger, bigger, bigger. And it'll diverge to infinity. So this is a formula you need. And you can also use this one as far as partial sums go, because it is possible you could see a problem where you just need to add up, the first 50 terms of a sum. And you can obviously do that if you want to add up 50 terms manually or with the calculator, but formula makes it a lot easier. So there you go. All right, so let's find the sum of this geometric series. Now this one, notice we have an alternating series, so signs are alternating. So now to find the common ratio, and you may remember this from algebra, we really just need to take any two terms, consecutive terms, and divide. So divide, say, 20/9 divided by -10/3. and maybe even easier than that, we could factor out a 5. Let's do that first. So 5 minus 2/3 plus 4/9 minus 8 uh, 27ths plus dot dot dot. And so now we could divide 4/9 divided by negative 2/3. You get the same thing, but it makes things easier if we factor out the 5. So we want this first term to be a 1. Um, and so that will give us negative 2/3. Yeah. Yeah, negative 2/3. So R is negative 2/3. So A is 5. So we get 5 over 1 minus negative 2/3. And that will give us 3. That's all there is to it. So probably don't do this part. Probably factor out the common or the factor out this first term first. So you want your first term to be 1, whatever that is. Factor it out, and then you can get the common ratio. You have your A and your R, and then there you go. So there's the sum of that geometric series. Okay, so let's do this one. So this is a problem that you may have seen. Maybe in middle school. I'm not sure. But how do you get these repeating decimals into a fraction? That's really what we're asking. So let's write this. So get the non-repeating part out. So the 2.3. Now we have 0.017 repeating. So this would be 2.3 plus 17 over 1,000 plus 17. Now you're going to add 2 zeros to this. So 17 over 100,000 and so on. All right. So now 2.3, you're just going to leave alone. Don't worry too much about it. I mean, you can write 23 over 10 if you like. Now factor out the 17 over 1,000. And we have 1 plus 1 over 100 plus 1 over 10,000 and so on. And so this will give us our common ratio. So A is 17 over 1,000. R is 1 over 100. So this will go to 2.3 plus 17 over 1,000. 17 over 100, 17 over 1,000 over 1 minus 100. Now, probably just get a calculator to do this. That gives us 2.3 plus 17 over 1,000 times, and put this in the calculator, you get 100 over 99. And so that gives us 2.3 plus 17 over 990. And then you put that in the calculator, convert it to a fraction, and that will give you 1147 over 495. Okay. Now, you may have learned this. I think I've taught this in a class before, more of a remedial level math class, I guess, where we have to convert this. We don't go into the geometric series. Really, what you can do is however many zeros you have before the repeating starts. So if it was, say, we'll just do 0.1717, well, 17 repeating, that would be 17 over 99. If you have 0.017 and the 17 is repeating, it would be 17 over 990. So you can put whatever however many you have, and if it was, let's say, 0.178 repeating, then it'd be 178 over 999. So it's kind of one of those things you can, however many you have repeating, put that many nines, and then if you have zeros in front of it, put the zero there. So that's kind of a shortcut without doing the geometric series. But the geometric series is useful depending on how far in math you're going to go. Geometric series come up quite a bit, so it's useful to be able to work with those. Okay, so now show that this series is convergent and find its sum. Now, what can we do with this? So if you add up these terms, I don't think it will tell you much. So you could write out these terms. So when n is 1, this would be 1/2. When n is 2, that would be 2 times 3, so this would be 1/6. When n is 4, that would be 4 times 5, so that's, we did 1, 2, 3. When n is 3, that would be 1/12. When n is 4, that would be 4 times 5, so 1/20th, and so on. So that doesn't really help too much. This is not a geometric series, so we can't use that trick. Now, you might recognize this from an earlier section when we were integrating, so we could use partial sums. So let's see what happens when we do partial sums with this. So remember, we have two linear factors, so that gives us an a over n plus a b over n plus 1. Let's get rid of the denominators. So a times n plus 1 plus b n. And with linear factors, it's pretty easy. Just substitute a couple of things in for n to get rid of each factor. So plug in n equals 0. That gets rid of the b term. A equals 1. Plug in n equals -1. That'll get rid of the a term. And we get b equals, or 1 equals negative b. So b is -1. So this becomes, it's a -1, -1. So this becomes 1 over n minus 1 over n plus 1. So now let's write this, let's write the terms of this sequence. So 1 over n minus 1 over n plus 1. So when n is 1, we get 1 over 1 minus 1/2 plus when n is 2, we get 1/2 minus 1/3. So n equals 1, n equals 2, n equals 3, we get 1/3 minus 1/4. And maybe you can see what's going on now. We have, if we regroup these terms, or reorder them, so we're just going to switch the 1/2s, we're going to switch to 1/3. But you can probably see it without doing that. These two cancel out. These two cancel out. 1/4. The next term will be a plus 1/4. And so these are zeros, zeros, zeros. So this is just equal to 1. And that's it. That's all you got to do. So this is what's called a telescoping series. So when you have, after a certain point, all the terms just cancel out. That's called a telescoping series, and it comes to a finite number. So now, it's not obvious when you look at this, but if you kept going, maybe get on Excel and you could, well, be kind of, you could do it. Just plug in the formula and you could do it on Excel, or you could write a program to do it somehow. But you'd see that these terms are going to get closer to 1 the higher n gets. Okay, and now let's look at a couple of theorems here. So how do you know if a series is going to diverge? If it's a geometric series and r is greater than 1, we automatically know it's going to diverge. We have this theorem here. If the series is convergent, then the limit goes to 0, or the limit as n approaches infinity of the terms goes to 0. So the terms will go to 0. Now, one property of logic, or one truth about logic, if you have a truth statement, an if-then statement, you can negate both and reverse the order. So if let's reverse the order. So we're going to put this one first, and we're going to take the opposite side of this. So the opposite of the limit goes to, or equals 0 would be the limit does not equal 0. So if the limit as n approaches infinity, a sub n is not equal to 0, then, now what's the opposite of this one? If it's not convergent, it is divergent. So then the series from 1 to infinity of a sub n is divergent. So that's the more useful way to think about this, because normally we want to know if it's convergent. So we don't know that ahead of time, but we might know this ahead of time. So this is probably the more useful way to phrase this. So if you look at the terms and they don't go to 0, then you know it's divergent. Now, it's not necessarily true that if the limit goes to 0, then the series is convergent. That is not necessarily true. One classic example is 1 plus 1/2 plus 1/3 plus 1/4 plus 1/5. So these terms go to 0, plus dot 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 plus 1 over n. So as n goes to infinity, that's going to go to 0. But this series, so we could write this as 1 over the sum of the 1 over n terms, that goes to infinity, so divergent. So that is the classic example of a series where the terms go to 0, but the series is actually divergent. So the reverse statement is not true, but you can always negate the two parts of the if-then and reverse the order. That's called the contrapositive. And the contrapositive of a statement is always has the same truth value as the original statement. All right, so a test for divergence, which is kind of stating this part. If the limit does not exist, or if the limit, that's just infinity. If the limit is not 0, then the series is divergent. So the limit may not exist. So one of these would be, say 1 minus 2 plus 3 minus 4 plus 5 minus so on. So the limit does not exist, because if we look at the positive terms, it goes to infinity. If we look at the negative terms, it goes to negative infinity. So the limit does not exist. And so this is going to be divergent. The other one, if the limit is not 0, which we could just, any geometric series that goes to infinity, that also works. All right, so determine whether this is convergent or divergent. So let's take the limit as n goes to infinity, n squared over 5n squared plus 4. Probably remember from calculus how you would do these. So we'll divide each term by n squared. So take the highest exponent, n squared, so that gives us 1 over 5 plus 4 over n squared. And so then plug in big numbers for n. Imagine plugging in big numbers for n. This goes to 0, so we end up with 1/5. So the limit as n approaches infinity of n squared over 5n squared plus 4 is not 0, so that tells us that this is divergent. Okay, so kind of a lot of new stuff in this section, and we're gonna see a lot of new stuff as we go along in chapter 11. This, kind of like the integration, where this is a lot of stuff and it's a lot of new stuff. And like the integration, we're going to be learning different techniques for doing this. So the key part is to practice it and get familiar with what to look for. If you have any questions, please let me know.